All right, so we've been talking about volumes of regions rotated about the x-axis or lines parallel to the x-axis. So today we're going to be talking about what happens when we rotate regions about the y-axis. And I'm going to get away from the washer method a little bit, so we're going to backtrack and go just to solid figures again. So we're going to start with the example. We want to calculate the volume of the region enclosed by y is equal to x squared, x is equal to 0, and y is equal to 4. I kind of sketched what that would look like up here on my board. And I want to know what is its volume when we're rotating it about the y-axis. So here's my region. I want to imagine, all right, well, if I'm rotating about this y-axis, it's going to look kind of like almost like a bowl shape. So I'll draw what that region's going to look like on the other side. Something like that. Fill that in. So I want to know what this volume is going to be. So when we're rotating about a vertical line, either it's going to be the y-axis, or tomorrow we'll talk about other vertical lines. There's one thing that I have to keep in mind is now I'm not going to be integrating in terms of x's, I'm going to be integrating in terms of y's. So this is kind of a concept that we were talking about when we were doing area between curves. That's going to come back again. So I want to think about this in terms of a cross section for a second. So we're going back to, like I said, the solid. So its cross section, if I were to kind of take a chunk out of here, is actually going to be cylindrical in nature. So its thickness or its height, we're going to say, is going to be delta y, or the change in y. And something that we also have to think about now is the radius. And the radius is going to look a little bit different. So the radius of the face of this cylinder is going to look something like this. So before we get into that, I want to talk about what the actual kind of setup for these problems is going to be. Pretty similar to what we've been talking about. But since we're talking about like a delta y situation or a change in y, our setup is going to look a little bit different. So it's still going to be the volume is equal to pi times the integral. But since we're talking about the change in y, or y values here, we're going to be integrating in terms of c and d. Before we were integrating in terms of a and b, which represented x values. C and d are going to be representing y values. And here we have our radius squared, but our radius is going to be in terms of y. So the radius in terms of y squared. And normally we would put dx here, but since we're rotating about the y-axis or about a vertical line, we're going to be talking about that in terms of dy, or the delta y. So let's talk about the radius of this particular cross-section. So the radius is this distance from the y-axis, since that's my axis of rotation, out to my curve. Or I could have a radius down here that's a little bit smaller, or I could have a radius up here that's a little bit bigger. So this really is just representing some x distance, right? From the x value of 0 out to this curve, x value of 0 out to this, x value of 0 out to here is just some x distance. So if we think about this in terms of how we were talking about it with the area between curves, we always started with our right curve minus our left curve. I'm going to start this kind of the same way. The right side of my curve is just this x value, whatever this x value is along this curve, minus the axis of rotation, in this case is just 0. But we said that in terms of our integral, we need to know what this is in terms of y. So the radius of x minus 0 really isn't going to help me when I go to actually integrate it. I need to know what this is in terms of y. Well, I've got a function up here, right? Y is equal to x squared. What if I were to take this y is equal to x squared and get it in terms of x, so then I could know what the radius of this actual three-dimensional figure is going to be when I rotate it. So let's take the square root of both sides. This is going to tell me that x is going to be equal to the square root of y. So that means that the radius, if the radius is the x value minus 0, well, the x value here is really the square root of y minus 0. So the radius in terms of y is actually the square root of y. And this is what I mean in terms of r of y. I'm going to go ahead and I'm going to use that in my integral up here. So I'm going to start by setting up here the integral, or pi times the integral from c to d. Well, what is c to d? Well, we said c to d was just some y value. So if I think about where the y value is that my curve was starting down here, well, the x value is 0, but the y value is also 0. Up here where my curve is meeting my boundary of y is equal to 4, well, that's easy. That's just a y value of 4. That's telling me that I'm integrating from the y value of 0 to the y value of 4. And then I'll go ahead, plug in my r of y, so square root of y squared dy. If I simplify that a little bit, pi times the integral from 0 to 4 of y dy. In your calculator, remember we were doing this with the area between curves, you can calculate this in terms of x. Your calculator doesn't know the difference anyway. So when you go ahead and type that in to evaluate, you get a volume of approximately 25.1327. All right, so let's look at another example. Get rid of all this stuff. So it's going to be a little bit different. So now we want to calculate the volume of the region bounded by x is equal to negative y squared plus 4. The line x is equal to 0, and I'm rotating this about the y-axis. All right, so I know that I probably want to see visually what this looks like. Well, when we usually graph, we graph something in terms of y is equal to. Right now, I have an equation in terms of x is equal to. So before I graph this, I'm going to manipulate this function a little bit just to get it in terms of y equals so that I can know what this is going to look like in terms of a graph. So bring the y squared over here. I'll bring the x to the other side. Take the square root. So it tells me that it's a little bit messy, y is going to be equal to plus or minus the square root of negative x plus 4. And you can use your graphing calculator to help you actually see what that graph is going to look like. I'm going to sketch this out down here. All right, and that is going to be, so 4 is 0. Make some marks down here as well because I'm going to need to know what the bottom half of the graph looks like. And then over here. And over here. So this is kind of what that graph is going to look like with that y is equal to plus or minus the square root of negative x plus 4. I am bounded by the line x is equal to 0. So I am bounded by this y-axis. So the region that I am going to end up rotating is going to be actually all of this. And again, just be careful when you're manipulating that algebraically. When you take that square root, don't forget you need to have that plus or minus because you need to have both the top and the bottom region. So if I were to take that and rotate it about the y-axis, I'll draw its kind of reflection over here, just so I can have kind of a good idea of what that's going to look like. So the solid ends up looking something like this, and you can kind of imagine that in 3 dimensions. So I'm going to start setting up my integral here. I'll figure out what I need to know. So v is equal to pi times the integral from, and now I need to know where my boundaries are. So if I'm thinking about my y values, because again, we're integrating this in terms of y, I'm starting down here at the y value of negative 2, and I'm ending up here at the y value of positive 2. So my integral is going to go from negative 2 to positive 2. And then I need to know what this radius is. So if I think about the radius of the cross section, the radius is going to go from my y-axis out to the edge of my curve. So, like I was saying before in the last example, the radius is just this x distance minus my axis of rotation, which is 0. But remember that in order to integrate in terms of y, we need to know what x is. Well, up here, I was given this equation in terms of x. So I know that the x value here is represented by negative y squared plus 4 minus 0, which is really just telling me that my radius is negative y squared plus 4, which, again, it's really the curve itself, or that function itself. So I'm going to be integrating from negative 2 to 2. My r of y is negative y squared plus 4. Make sure to square it and put my dy over there. And again, when you plug that into your calculator, you can again just kind of integrate in terms of x. So you should get a volume of approximately 107.2330. And that would be this entire volume of kind of this football shaped thing revolved about the y-axis. All right, we'll do one more example together. And then I'll have you try some on your own. So the last example is to rotate, or to find the volume of the region rotated enclosed by x is equal to y squared plus 2. And I'm bounded this time by the line x is equal to 0, y is equal to 1, and y is equal to 2. And I'm rotating that about the y-axis. So similar to the last one, I just want to get a good idea of what this graph is going to look like. So I'm going to manipulate this a little bit just to get it in terms of y equals. So y squared would be equal to x minus 2. That's going to tell me that my y value is plus or minus the square root of x minus 2. And again, you can use your graphing calculator to help you get what that graph is going to look like. Just go ahead and graph that down here. So put a point here, that's here and here. So this is my y is equal to plus or minus the square root of x minus 2. I'm bounded by the line x is equal to 0, which again is just the y-axis. But this time I also have boundaries in terms of y's. So I have a boundary of y is equal to 1 and y is equal to 2. And this is not the most accurate drawing here, but it'll look something like this. All right, so the region that I'm going to end up actually rotating here is going to be kind of this region like up above my curve. So if I were to kind of reflect what that's going to look like, I'll just kind of do a really quick sketch of what that's going to look like over here. So here's my kind of reflected curve. It's going to look something like this. All right, so then what I need to do is I need to figure out what my radius is going to be, because I don't really need to worry about what my bounds are. It's actually telling me what the bounds are up here with the y value of 1 to the y value of 2. But my radius is going to extend from my axis of rotation out to here, out to some x value. So my radius, again, is just x minus the axis that I've rotated about. But again, I don't want to know this axis in terms of x. I want to know this axis in terms of y. But again, since we're given the function up here, my function is already in terms of x equals. So my radius is actually just y squared plus 2 minus 0. Again, obviously that minus 0 doesn't really matter for anything here. So my radius is actually y squared plus 2, which again is just the function itself. So when I go to plug into my volume is pi times the integral from the y value of 1 to the y value of 2. Again, we were given that up here, of my radius of y squared plus 2 squared dy. And when you calculate that out, again, using your graphing calculator in terms of x, that should give you a volume of approximately 61.3658. And that would be the volume of that solid rotated about the y-axis. All right, so I'm going to have you guys try some problems on these. Let me know if you have any questions.